Hi everyone, I'm going to present the results of our study on the evaporation of phosphate species from calcium phosphate ceramics during high temperature treatment. Calcium phosphate ceramics are commonly used as synthetic bone graft substitutes to fill large bone defects, and the majority of products is used in the form of either porous granules or porous preforms. And most of these products have been subjected to high temperature, typically above 1000 degrees Celsius, at some point during their production process. And this step is typically used for consolidation, so sinter effects should improve the mechanical stability of the products, and also to induce phase transformations to obtain beta-TCP or hydroxyapatite or a mixture of the two, and sometimes also for combustion of organic pore fillers. The bulk phase composition of a ceramic implant determines the mid to long-term stability in the defect, so whether or not the implant is resorbable. And the surface composition determines the short-term biological response to the implant. For example, if the surface is coated with a highly soluble phase, we will observe a burst release of ions immediately after implantation. It can also change the local pH at the implantation site strongly. And if the material is bioactive, we can observe formation of biomimetic apatite precipitation on the surface, and thus a change of the ionic concentrations around the implant. Evaporation of phosphorus from calcium phosphates has been reported before in two studies by Nagai et al. And we also made some observations in our own laboratory when we produce alpha TCP at high temperatures at 1350 degrees. We observe a loss of phosphate, so we have to start with a lower calcium to phosphate ratio in the green powder blend in order to obtain the precise calcium to phosphate ratio we want to get after the thermal treatment. The aim of our current project was to establish a model for the evaporation of phosphorus species from calcium phosphate phases at high temperature, and we wanted to do this based on the thermodynamic properties of the phases involved. And after establishing the model, we wanted to have an experimental verification. The first step was to establish a list of all possible decomposition reactions for the phases calcium pyrophosphate, tricalcium phosphate, hydroxyapatite, and tetracalcium phosphate, releasing the gaseous species P, P2, P4, PO, PO2, P406, or P4010. This resulted in a total of 70 possible decomposition reactions. In the second step, we calculated the Gibbs free energy of reaction for all these decomposition reactions. In the third step, we calculated the equilibrium vapor pressure for the gas species in equilibrium with the two solid phases involved in the decomposition reaction. And in the fourth step, we calculated the Gibbs free energy of all possible solid state reactions involved, because the reaction products could also react with the starting phase, so we also had to take into account possible solid state reactions. The detailed results of our thermodynamic calculations are published in this paper. Just to summarize, our calculations showed that evaporation occurs from all solid calcium phosphate phases, and all phases are capable of releasing all gaseous species we considered in the decomposition reactions. So based on this information, we established a model for what happens when we subject calcium phosphate ceramics to high temperatures. And the first scenario we modeled was an open atmosphere. And this was important because in the first scenario, we assumed that the concentration of phosphorus gas species in the atmosphere never reaches saturation levels. So what happens when we subject, for example, a calcium pyrophosphate block to high temperatures in an open atmosphere? First of all, we will observe phosphate evaporation at the surface. So we will observe an increase of the calcium to phosphate ratio at the surface. And since all more calcium-rich phases than calcium pyrophosphate can form, we have to assume that TCP, hydroxyapatite, and calcium oxide can form at the surface. The process continues, and we will also observe evaporation from TCP and HA, but we also have to consider that we can form solid phases that are not stable in direct contact. So at the phase interfaces marked in red, we will observe solid-state reactions. And if we follow this cascade of reactions involving the evaporation of phosphorus and the solid-state reactions of unstable phase combinations to the end, we reach a stable condition once a surface layer has been established with a gradient from the substrate towards the surface of increasingly calcium-rich or phosphate-depleted phases. This is the only stable situation in which no more evaporation can occur and no unstable solid phase combinations exist. The second scenario we modeled was a closed furnace, which means that the concentration of phosphate species in the atmosphere will increase and eventually reach saturation. The first step of the decomposition is the same as in the open atmosphere. We will release all possible phosphate gas species and form a phosphate-depleted layer on the calcium pyrophosphate substrate. And this layer again can contain TCP, hydroxyapatite, and calcium oxide. But as the partial pressure in the atmosphere increases, we could show that some reactions will actually supersaturate the atmosphere for other reactions. And once the atmosphere is supersaturated, the decomposition reactions, for example, CPP to calcium oxide, will invert its direction, which means that calcium oxide will in fact start to react with gaseous phosphate species in a condensation reaction and form more phosphate-rich solid phases. And again, if we extrapolate this cascade of reactions and also take into account the solid-state reactions among the solid phases, we reach a stable condition when the surface layer composition is single phase. And the atmosphere is in equilibrium with the two solid phases, the substrate and the single phase layer on the substrate. So these are the two models based on thermodynamic calculations that show which surface composition we would expect in a closed or in an open furnace. And for the experimental validation, we developed a system based on pressed calcium phosphate pills of the size of a coin approximately. After the thermal treatment, we measured the surface composition of the top surface of the top pill, and we also crushed the pill afterwards to determine the bulk composition by X-ray diffraction. We observed the following results, starting with a relatively pure beta calcium pyrophosphate in the first two rows, marked in red. We observed almost pure beta CPP and only small amounts of beta TCP. And at the open surface, the one in contact with the atmosphere, we observed a massive increase of beta TCP, 25.2% in the first sample and 16.8% in the second sample. With the biphasic sample composition beta TCP and HA, we started with 81.7% hydroxyapatite in the bulk composition, and on the surface we observed 85.6% hydroxyapatite after the thermal treatment. So we also observed an increase of the calcium to phosphate ratio at the surface, although to a much smaller extent than with the previous composition. And the relatively pure hydroxyapatite showed an increase of calcium oxide at the surface, but very minor, and a decrease of beta TCP at the surface relative to the bulk composition. A second series of experiments was performed to test whether or not we can provoke condensation on the top surface of the stacked pills. So what we wanted to do was we placed some loose calcium pyrophosphate powder around the stacks. This decomposition reaction of calcium pyrophosphate to TCP generated the highest partial pressure of phosphate gases in the atmosphere, and would supersaturate the atmosphere towards all other solid phases. So when we process these samples, again at 1100 degrees for 36 hours in a closed furnace, we observed a strong reduction of the calcium to phosphate ratio at the surface relative to the bulk. So to summarize, first of all, our thermodynamic calculations showed that the surface chemistry is altered by thermal treatment of calcium phosphate ceramics by either evaporation or condensation during high temperature treatment based on the composition of the atmosphere. The extent of the surface modification depends on several technical parameters. For example, the ratio of the furnace volume to the sample volume. Also, the permeability of the furnace determines how quickly saturation of the atmosphere is reached. And of course, there are furnaces with active fresh air supply, which can be used to strongly affect the amount of evaporated phosphate. By using active ventilation or sacrificial calcium pyrophosphate material, we can now control the surface composition very precisely. We can either enforce evaporation to form a calcium-rich surface layer, or we can supersaturate the atmosphere and provoke condensation and thus form a phosphate-rich surface layer. As I have mentioned before, this study was already published in the Journal of the European Ceramic Society earlier this year. And in this article, you will also find all the detailed calculation results. I would like to thank my colleagues at RMS Foundation and at the University of Illinois in the US and at the University of Bern in Switzerland for their support. And this study was funded by RMS Foundation. And thank you very much for your attention.